Hi guys. We are watching this video, and because I'm not in class today, obviously I had to leave early. So what you need to do is take out your Unit 2 packet, and if you don't have a Unit 2 packet, it's back there on the table. And open up to page 5. We're going to learn about how minerals form. And as you guys can see, this is a beautiful geode with amethyst in it. Someone broke this open, and the space in here allowed these crystals to grow. So that's one of the ways that minerals form. So we'll be talking about the different ways that minerals form. All right. So next slide. Well, it seems like I've skipped one already. There we go. Minerals are made from elements. I believe you guys saw that in the video you watched. And you guys all know what elements are. They have a certain number of protons. They can't be broken down by normal chemical processes. They are basically the building blocks of all the materials that we have on Earth. And minerals are usually compounds, which means they're basically more than one kind of atom joined together in a chemical bond. I think you guys hopefully remember the definition of minerals. They're inorganic, they're naturally occurring. They always have a chemical formula. So that's what this sentence means. They're joined by a chemical bond. For example, quartz is SiO2. And I think we did talk about that. Calcite, which we'll see in class when we do our mineral lab, is CaCO3, calcium and carbon and oxygen. All right, so next one, hopefully you filled put these notes in on page 3. Oh, for goodness sake, there we go. All right, rocks are made from minerals, and therefore rocks don't have a specific chemical formula. We do name rocks based on the chemical composition of the rock, as well as how it formed, but the chemical composition can vary. So we can call something a granite, and it might have white and gray and a few black minerals in it, but this other rock over here has a lot of white and pink and yellow minerals with few black minerals in it, and they're still both called granite. Minerals, on the other hand, have a set chemical composition. It's always in the same ratio, okay? So we're going to talk about crystallization, and that's the process by which we get minerals. It's by which atoms, ions, or molecules are structured together in a regular, repeating geometrical arrangement. One of the other parts of that definition of a mineral was that it has a chemical structure and a crystal shape. So the way that the atoms bond together will give that mineral its crystal shape. Okay. All right, so that was number 4. That's called crystallization, and it happens in 3 ways. And by the way, you hear that word crystal and you think of a beautiful crystal. Well, crystallization of minerals, that's always when the atoms get together to form the mineral, but you don't always get a beautiful crystal. In fact, getting a really beautiful crystal is rather rare, because in nature, all the way these things are formed, usually there isn't enough room for that mineral to grow and get big and beautiful. Sometimes there is, but not as often as usually. It's kind of, just kind of trapped in among other minerals. And so you don't get that same mineral shape, that same crystal shape. All right, the 3 ways in which minerals form, you've probably been writing this down while I've been talking. Crystallization of a magma, and magma is a melted rock. And if you guys remember, we said during plate tectonics, but it was a while back, magma is melted rock that's under the Earth's surface, and then we call the same exact stuff lava when it flows onto the Earth's surface, usually in a volcano. Crystallization of materials dissolved in water. So if some materials, like think of salt being dissolved in water, and if you guys let a glass of salt water just sit out for a while and the water starts to evaporate, you'll get some cool square cubes, or some cubes at the bottom of the glass, which is the salt coming together after it's been dissolved in water and becoming a solid again. There's also crystallization from metamorphism, and that's basically talking about like how a metamorphic rock forms. It's heat and pressure. Usually it gets buried, and it's maybe even in a convergent boundary, and the plates are, crunching together, and that heat and pressure builds, and that will actually cause the atoms to rearrange and make new crystals. And so that's how we get crystals from metamorphism. All right. I'm going to keep moving on. Remember, whoever's running the slideshow, you can ask them to pause if you need a little more time to fill this out. Here's some examples of really cool crystal shapes. Galena is a neat, you'll see this in our lab. It's very shiny and silver and very dense. Pyrite, you guys probably know, is fool's gold. Pyrite will break into cubes, but it actually grows in these weird hexagonal type crystals. Okay, here's a hexagonal beryl. Galena makes cubes. Calcite, scalenohedrons, which are like, they're kind of a crazy shape. It's like you might want to use that to make the tip of a sword out of, right? And so there's really neat shapes in the crystal world. We'll see some of them. This is a pretty one down here as well. Minerals that form from magma and lava, that's called an igneous rock. So we get these minerals in igneous rocks, and they form as hot magma cools. I was going to record or make sure I didn't go over on my time. They form as hot magma cools slowly inside the crust, and then they can cool as lava hardens really quickly on the surface. That will make much smaller crystals. We'll talk about that in a minute. But when these liquids cool to a solid state, the crystals form. The atoms basically find each other. They have negative and positive charges, and they will find each other and make really cool crystal shapes, or a new mineral. They'll make a mineral out of a liquid magma. The size of the crystal in these igneous rocks, and we are on to number 7 right now. That depends on several factors. It depends on how fast they cool, the rate of cooling. And like I said, if it cools underground, it's going to cool more slowly and usually get bigger crystals. It also depends on the amount of gas that's dissolved in the magma. Most magmas will have gas, and that will determine how quickly it forms and how slowly it forms, and the chemical composition of the magma. So what are the minerals that the magma is made up of? All right. Obviously, that is a huge factor in what kind of crystals we're going to get. So minerals from magma and lava, again, deep below the Earth's surface, these magmas can cool over thousands of years because they are very slowly dissipating heat out through the rocks. And the atoms will come together and form these different kinds of minerals, beautiful minerals. And it kind of depends on the temperature, the melting temperature of the mineral, and when it will form as the magma is cooling, at what temperature it will form. So the slow cooling leads to the formation of larger crystals. This is a granite, and you can see that's a feldspar, that pink crystal. There's some quartz in here. There might even be some white feldspar, and then there's some black iron. We call those ferromagnesium minerals. Growth will continue in a nice regular pattern if it's undisturbed, and you get minerals that you can see with the naked eye. So we can look and see, and all these different minerals in here. I can identify them just by looking at them. If the magma comes out of a volcano or a vent and it cools very quickly on the surface, there won't be time for these crystals to form, the minerals to find each other and form really nice minerals. The atoms, I should say, to find each other. The rapid cooling leads to much smaller crystal formation. You usually can't identify the minerals in this cooled lava unless you cut it into pieces and kind of glue it to a little slide and grind that rock down so you can see light through it in a microscope. And then I can look under the microscope and figure out what the minerals are inside the magma. All right, so magma erupting to the surface becomes lava. It cools really quickly, and we get minerals forming, but they're very small. They're too small to identify with the naked eye. All right. Now that I want you to stop here. We're going on to the next way to get minerals, to get crystallization. What's the definition of a solution? Can you give an example of a solution? And I'm not with you, but can anybody tell me what a solution is? If anybody said like Kool-Aid or soda, now if you have a drink right now that has some kind of a sugar in it and food coloring, that's a solution. It's anything that's going to be dissolved in another substance. So it's a mixture in which one substance is dissolved in another. And if you remember your chemistry, a mixture means they're still separate. You can see that this is salt water. There's a sodium ion. There's a chlorine ion. This water is going to taste salty, even though they're not together making salt because they're both in here. It's still going to have the properties of salt, taste of it. And when you let this water dissolve, the Na and the Cl, the sodium and the chlorine, are going to attract each other and form little salt cubes. Okay, so that's what a solution is. And this happens as well out in nature. Okay, when elements or compounds that are dissolved in water form, they eventually get together and form a crystal, then that's what we call crystallizing from a solution. Minerals form in this way underground or in bodies of water. There can be groundwater flowing through a rock, and the water, that water will get warm if it's down below the surface, far enough. It can dissolve minerals, and then somewhere else it'll actually leave these minerals. It'll deposit these minerals, which is kind of cool. All right. There's a geode. You guys have probably all seen a geode. There's one in my room. So if you look over by where the pencil sharpener is, there's a piece of a geode that looks very much like this. That's a penny, I think, just to give you guys a sense of size. And that's a hollow rock that's often lined with mineral crystals. What happens is it formed when water containing these dissolved minerals, in this case quartz, which has something in it that's making it a purple quartz, which we call amethyst. That water will seep into a rock or a crack in layers of different sediments or into an actual crack in a rock, and that liquid will slowly, the crystals will slowly form in that liquid, and they have some space to grow. So that's why you get these beautiful crystals. Okay, so there's all these crystals lining the edge of this material. And you guys can kind of see that's all quartz there too. So the quartz is growing out of this material. Now, this is an awesome picture, isn't it? This is minerals from solution, showing what can happen in extreme conditions. This is in Mexico, Chihuahua, actually, and it is called, and I've forgotten, what is the name? It's the cave of the crystals. I have it on another slide. But this is the biggest mystery. These are the biggest minerals we've found anywhere in the world. They're a form of gypsum. You'll see what that is later. But this guy has all this stuff on because these are formed in a very gaseous environment. It's hot, and there's some dangerous gases in there, and those gases have allowed this very moist gaseous environment has allowed these crystals to get outrageously big. There it is, the Cueva de la Cristales, Cave of the Crystals is what it's called. And let me hide that thing so you guys can see it, in Chihuahua, Mexico. And these guys also still have their suits on. I have a picture. It might be the next one. Maybe I don't have it. Let me see. Of a guy who doesn't have anything on, and I'm like, whoa, nope, I guess I don't. He doesn't have his mask on, but most of them do. I guess I went way too far. Oh, there he is. So he's kind of up a little higher. You can't go in these caves. They are actually restricted now because you just can't walk into these. I don't know how long he stood like that. But the more people they let in, or the more air they let in, then those crystals will actually start to break down and they won't be there anymore. So it's not like we can move these crystals. They are very hydrous. They have a lot of water in them. And so they need to stay in that environment. And they probably formed when the whole cave was actually flooded with water. It might have been filled with some kind of solution that had the materials for these crystals in it. So it's kind of cool, that they're standing on these things, but very, very rare, very unusual. And I just can't even imagine seeing a crystal that big. Okay. All right. On to number 13, minerals formed from evaporation. You can, get these by dissolving salt into water. You guys can make sugar crystals, even though that's not really a mineral, because sugar is a biological. Remember, it's organic. It comes from sugarcane, so those aren't really considered minerals. But you can make rock sugar if anybody's done that. You can also do that with salt. Let the salt evaporate slowly in the water, and or the water evaporate out of the salt solution, and you'll get little salt crystals. So you allow the water to evaporate. Salt crystals left behind. Salt is the official mineral word for salt is called halite. If I was there, I would show you. I have a great big cube of salt, like this big, rock salt, they call it, and I'll show it to you next class. But But that's basically how there are many deposits of salt, and they're usually from ancient seas. The sea came in, then sea level went down, the sea slowly went out, or maybe the water got stuck on this plane and it evaporated, and salt crystals are left behind. So the salt that you eat, usually it's been kind of plowed up in one of these salt fields. There's even deposits under the ground that they can pull out. But they actually even make this. They'll have areas next to the ocean where they'll let the salt water in and then cut it off and then let it evaporate, and you get these fields of salt. Okay. You guys have probably seen salt that's got a lot of different colors. That's because it's got some other minerals in there, like the actual structure. The sodium's been replaced by something else in some of this, some of the areas. And so there's different kinds of salts, and, they do taste pretty much the same. So it's not like you can see a big difference. But when pools of salt water dry up, the excess salt of the solution falls to the bottom, forming the mineral halite. And so halite is what we love. We eat halite all the time. So you guys eat a mineral every day, and we call that mineral halite, as salt, or the chemical name is sodium chloride. All right, sodium and chlorine mixed together. Now, this is a really cool one. This is a type of geode, and it was in a solution, and this is actually showing it upside down. It probably grew, the liquid probably dripped off, but I'm not positive about that. But isn't that beautiful? Isn't that a gorgeous crystal? At the end, I'm going to ask you what's your favorite crystal that you saw, and maybe this will be it. And I can't remember what this is called. I thought I wrote it on it. I'll have to tell you guys later. Minerals from solutions can also do this. They can also seep their way into rocks. These used to be rocks in the ground, part of maybe a mountain chain. And there's cracks in the rocks because of plate tectonics. Plates are always under pressure. And so they might crack, and then the water will seep its way in. And the underground magma can heat up the water to super high temps. It'll dissolve more things that way. Elements and compounds that form a mineral dissolve in this hot water. The water solution will go into these veins and cool, because it's in much smaller amounts now. And so it cools off in the rock, and the crystals will form. And this is how we get what they call veins of precious metals. A vein is a narrow channel or slab of a mineral that is different from the surrounding rock. This probably isn't very valuable. It's probably just calcite or quartz. But this, you can tell, that's gold. That's a gold vein. Gold has been dissolved in really hot water, and that water flowed into this rock, kind of got stuck there, eventually cooled, and the gold precipitated out. And that vein is a great place to get gold because it's concentrated. And so it'd be worth someone's time to pull that gold out of the rock, to follow that vein down into the mountain and, make some money off of it. But that's how we get a lot of these pure mineral veins. And you might have heard of that, veins of minerals. Okay. So that is, where we go mining tends to be where this hot water solutions has concentrated minerals. So this is actually showing you guys down on a mid-ocean ridge. This is a mid-ocean ridge. I don't know if you guys can see that, but that's black smoke coming out of a hole in this basalt. Okay, this is the magma of the ocean floor. That's brand new, or that's ocean crust, ocean floor. And there's super hot water coming out of here. That is extremely hot water. It has dissolved a lot of the minerals in the magma, and they happen to be iron-rich magma. You guys remember the ocean floor, has a lot of magma in it, or a lot of iron in it. And so this comes shooting up. It's crazy how hot this can be. So this is in an undersea vent. There's magma probably very close to the surface down there. Here's an example of this. So here's the magma coming up, and the water is circulating around in this rock. This is probably under the ocean. It might not be, but it could be. And the groundwater will actually boil. And actually, this looks like it is on land because it's popping up. So here's the hot springs where this hot water comes shooting up to the surface. Cold water comes in down here, gets heated up here, and all along here is where you'll find the water that's going to dissolve gold and silver. Various elements and metals will be deposited on veins along this hot springs area. So, we don't need to know that, but it's just kind of interesting to see how that happens. Okay. All right. Last one, minerals from metamorphism, new crystals or what we call recrystallization can form during metamorphism, where pressure and temperature are increasing. This is causing atoms or molecules in a rock or mineral to rearrange into a new chemical structure, okay, a new crystal structure. So this is a rock that already has minerals in it, but when a rock is being put under increased pressure, sometimes the minerals want to take up less space because maybe it's in a convergent boundary and the plates are squeezing together, like India and um, Asia, where the Himalayas are being formed. Down deep, where the Himalayas are being pushed up, there's probably a whole lot of metamorphic rocks being formed and a whole lot of recrystallization happening very, very slowly. Remember, it doesn't get hot enough to melt it. If it melts, it becomes a magma, and then you have, recrystallization. You have crystallization from a magma. This is metamorphism. The minerals the atoms in them will actually move around, and they can form what we would call a new mineral. Sometimes it just goes from a bigger mineral to a flatter mineral, which we'll look at some micas. I don't know if you guys have ever seen a mica, very flat, really cool. You can see through it. It's usually pretty clear. And so the micas make up a lot of metamorphic rocks because they take up less space. So they're being kind of scrunched. Sometimes it's just temperature. In that case, they're not trying to take up less space. It's just being cooked up just enough to change it without melting it. It's like kind of, when you get a hard boiled egg, you guys know what an egg looks like, and then you put it in some hot water and it will change, right? It'll look very different than the original egg. And so you can kind of think of it like that. I like to imagine that you have a bunch of like chocolate and vanilla, chocolate and white chocolate chips, and you squeeze them together as a ball in your hand. You'll still see the black and white colors maybe, but you'll change that shape. And if you squish it down enough, they can become very flat. And sometimes the colors will kind of, blend together. But, we don't, they get warm and they might melt a little bit on the edges, but the whole thing doesn't melt. And you just kind of rearrange the atoms that way. So the process, it says, can be illustrated by observing how snow recrystallizes to ice. I got to quit touching there you go, without melting. So you can see that, like ice, snow can, become ice if you guys ever, you want to plow maybe you want to go shovel the driveway, but someone leaves in their car, maybe comes in and out on the car before you can shovel the snow off the driveway. And then you go to shovel it and it's like that snow has turned to ice, right? Because it's been pressurized under those tires. And now you have to scrape off the darn ice. I don't know if you guys have ever done some snow shoveling, but if anybody has, where a car has driven over the snow, you know what I'm talking about. It becomes very hard, and then you have to scrape it off instead of just nice fluffy snow because it has been put under a lot of pressure. Okay, but we didn't have to, didn't change the temperature of it that time. So here's some cool metamorphic crystals. We'll look at these when we do metamorphic rocks, but this is a rock we call a limestone. It's made from organisms that they can be big, like you see this big shell, and they can be tiny little organisms in the ocean waters that make their little teeny shells out of calcium and carbon and oxygen that's in the ocean water. And when they when they die, they fall to the bottom of the ocean and they build up over time and make a rock we call a limestone. It fizzes when you put acid on it. It'll be kind of cool to see that. It's made of the mineral calcite, which will also fizz. In class, when we have calcite, I'll give you guys a diluted hydrochloric acid, and you put a drop of it on calcite and it will bubble. It's basically freeing out the carbon, and it's making carbon dioxide, and it bubbles off, which is kind of cool. It's a neat looking rock, but it's kind of an ugly color, but it's cool if you see shells, but most of the time you might not see the shells. It can be very boring looking. When you put it under increasing temperature and pressure without melting it, those crystals will rearrange into beautiful white calcite crystals. And so that kind of ugly rock becomes what we call marble. You guys have all seen marble. It's white, maybe with gray stripes through it. It's very beautiful. We use it for a lot of things like tiles and floors. Oh, I wasn't quite done with that. This is another really cool mineral that forms when you put rocks under or minerals under, or any kind of rock actually, under some kind of increased pressure and temperature, this is garnet. I don't know if you guys have ever seen garnet. Garnet is a semi-precious crystal. There's a lot of jewelry made out of it. If you see red jewelry, a lot cheaper than a ruby because there's a lot of it, but it's still not easy to find good, clear crystals of garnet. But you might. I'll bring some in. I have some garnet jewelry. And the only way you get garnet is through metamorphism, through a rock being recrystallized, put under some increasing temperatures, and the atoms form together to form this beautiful red crystal, okay, called garnet. This is sillimanite, I believe, or kyanite, one or the other. And kyanite, same as this, higher pressures and temperatures than garnet. You increase those temperatures even more, and you get this beautiful blue crystal forming. So it's kind of neat. Metamorphic rocks are really probably the most beautiful rocks because you do get all these kind of cool crystals forming. This is when you just have pressure, maybe not so much temperature, but pressure. This rock could have looked like this. Now it looks like this. And you see all these little folds. This rock is trying to take up less space. And so you've got these veins of quartz. You probably have a lot of micas in there. This is a layer of garnet, as you guys can see. So it did go up in temperature a bit. And this has all just been compressed. And these minerals are all oriented flat because they're trying to take up less space. Okay. So I hope you guys got that. I think this is it. So this is what we learned. So you guys should have learned the 3 ways we get crystallization, but it's basically, atoms coming together to form a new chemical compound. And that's what we call a mineral. And so some of the things we'll look at, there's kind of normal, ordinary names for them, but they also have mineral names as well, like salt is called halite. And what affects the size of crystals that form as magma cools? I'm not there to see if anybody remembers that, but remember, it's affected by the composition and by the time it took to cool. So the time that it cools. What are 2 ways the minerals form from solution? So you guys can go back and look at that. So we can, when we have a solution, we can either have it crystallize out of the water, right? Inside, inside like a vein where it will crystallize, and we can have it evaporate. The water will evaporate and the crystals will form because they're left behind. And then how do rocks crystallize by metamorphism? We would need increasing pressure and temperature to do that. Okay. So I think that's it. And we're going to start looking at beautiful pictures of minerals. After we look at this, this is a map showing where things are. So if you guys remember from the video we watched, if we watched the video in your class, minerals are not evenly distributed throughout the earth, nor are elements. This is really more elements, but sometimes we do have minerals that are only formed from one element. Can you guys think of a mineral that's formed from just one kind of atom, one element? If you look on here, you can see some. You guys have probably heard of zinc, lead, gold, silver, copper. Here's copper. Cadmium. They're all elements that do make minerals, even though they're only made from one kind of atom. And those are called native elements or native minerals. So they just literally are one type of element. And you can see these throughout, but a lot of the minerals that we use are compounds, but this is just a few of them. Iron ore. So you guys can see we have lead and cadmium and zinc and iron in the United States, but we don't really have much copper. I mean, we do have some copper, but not as much. All right. So we'll look at that later. Okay. Now I just realized when I show it like this, when I'm making a video, I can't really see the names of all these things, which I have below. Some of them I put on the film, but this is called the fire opal. This is an opal. And opals are kind of weird. They don't have as much of a crystalline structure as most minerals do. And that's why other minerals can actually be incorporated into the crystal structure, and you get these really crazy looking, beautiful shapes inside the opal. Obviously, there's a light shining on this. This is pretty small. I don't know if you can tell that. There's not really a size, but it's sitting on another rock. But isn't that gorgeous? If you shine the light on it, that's the fire opal. Again, if there's something you really like, you've got to write down what your favorite one is, and we'll go back through at the end. This is a fluorite. Fluorite is a very common mineral. You guys are going to see it in our lab. This just happens to be a really cool sample of it. Okay, it usually grows. Well, this is the way it grows. It breaks in these really cool pyramids. It's like a double pyramid stuck together, but it grows in this crazy cube straight structure. What you're seeing is one big fluorite crystal growing, and then there's another one that's growing off the side of it. So that's a purple fluorite. Fluorite comes in many different crystals. This is simply quartz, SiO2 or quartz. I know I've mentioned it a lot. It's the most common mineral on the Earth's surface. It's hard. It's got a you guys remember Mohs hardness scale? It's got a hardness of 7. So it really is pretty hard. So it shows up a lot. But this one, what happened is quartz is SiO2, so a silicon atom with 2 oxygen atoms. And sometimes that silicon atom will be replaced by another atom that's a similar shape and maybe the same charge. And this one's been replaced with titanium. This is a titanium quartz. Isn't that so cool, though? It gives off all these colors when you put it in the sunlight. This is another opal. Opals are pretty cool, but they're the most amazing minerals. This is called, which one is this called? Oh, this is called the Galaxy Opal. It also isn't very big. It's only about this big, but they've taken a picture of it with light shining through it, and it's just beautiful. This is called the Galaxy Opal because it looks like these are some nebulas where stars are made, and there's some stars. It looks like like we're seeing galaxies in there. And of course, it's been polished. They don't naturally occur that beautifully shiny, the opals. This is a amethyst geode. Amethyst is a quartz crystal. You can see here this big giant quartz crystal that doesn't have the material, which, shoot, I forgot what it is. I think it's manganese that makes quartz purple like this, but this is the biggest geode in the world. And I believe it is housed in the South American country, and I can't remember what it is. If anybody wants to know, I'll tell you. But this is the biggest geode anybody has ever found, and it's just coated with these beautiful amethyst crystals and a couple of gigantic quartz crystals as well that don't have. They probably came later. They don't have the manganese or whatever it is. They might have been from a water that leaked in a little bit after most of this had formed. That almost looks like a galaxy, doesn't it? This is, oh good, I put this on here, scolecite. So this is SCOLECITE, scolecite, and it forms these incredibly delicate, straw-like crystals. They do break pretty easily, but they are hard. They're pretty solid. They're very solid, obviously, and they're hard, but they will break off depending on how thin they are. But that's scolecite in its crystal form. This is tourmaline. This is called a watermelon tourmaline for obvious reasons. The different elements that have been part of this element or this mineral tourmaline have given it this red in the middle and the green on the outside. And there's quite a few of these out there. You can buy these. They're pretty cool. But that's a watermelon tourmaline. This is called uvarovite, and I like this one because it looks like lime jello. I think this looks like lime jello. So here's uvarovite, this really cool lime green. And it's growing on another rock. Most of the time when you see crystals in nature that are growing, they're growing on other minerals or on a rock, and there might have been a space in the cave, some kind of a crack in a rock that had room to grow. This is the Colorado state mineral. This is called rhodochrosite, RHODO, and then crosite, CROSITE. And it is found in one area called the Alma Mine, and I believe it's down near Cripple Creek. And there was a whole bunch of this found in this area, and in these big gaps in the rocks, these cracks in the rocks, and in some caves. And so this is just gorgeous. It's a beautiful cherry red color, and you can see the lines through here. If I hit this with a hammer, it will break in cubes. And next, when we get back from spring break, we'll be talking about the physical properties of minerals and how to identify minerals. And the fact that it breaks in these cubes would be one of the identifying properties of rhodochrosite. This is another opal. This is called the ocean opal, or it's called ocean in an opal. It's famous. I think this one sold for $25,000. One of those other ones sold, I think the Galaxy one for $40,000 maybe. But again, you can see the size is pretty small. It's been polished, and then you shine some light through it. But this really does look like seaweed, doesn't it? Maybe a crab up there. They call it the ocean in the opal because, and it's also got this beautiful blue color. So that's kind of a cool one too. All right. I'm trying to see how much time we've got here. Next one. This is again quartz, and this is quartz with what has it got in it? It's called an aquamarine, but aquamarine is just the name for this blue, light blue quartz. But isn't it just beautiful? Okay, this is actually might have titanium in it as well, but that's just a gorgeous one. This is an opal that it's a fossil. You guys can see this is a tree. The fossil has been opalized. So what happens is liquids, a solution will be kind of going through this fossilized tree stump, and it will replace some of that material with an opal, and it's just beautiful. You can see how it just shines out from the structure of the original tree trunk. That's not wood anymore. That has been replaced by a mineral that is of similar color, obviously, but it really isn't. It really is a mineral now. Okay. Now I just wanted to show you guys some quartz. This is smoky quartz, and I have another picture in a minute of a bunch of different quartzes. Quartz is, like I said, it's super abundant, and there's lots of different versions of it because lots of different elements can take the place of the silicon. There's a lot of elements that are around the same size as the silicon atom. And so there's a lot of that happening out there, but this is a beautiful smoky quartz. I'll show you a bunch in a minute. This is another opal. This might be our last opal. This is called Lightning Ridge, the Lightning Ridge opal. It's from Australia. And I don't remember what mineral that is, but that's a mineral inside this clear opal that is giving it this gorgeous, it looks like black lightning, but it is called, I think it's called the Black Lightning opal. Okay. This is bismuth, and you can actually grow this. This is a mineral, but I think you melt it and then you can let it grow, and it grows into these crazy, really cool forms. You can watch, there's videos on YouTube about how to grow bismuth crystals, but that's a pretty neat one too. But that's pure bismuth. Okay, Bi on the periodic table. These are all quartz. I told you guys when I do this thing where I'm going to give out little pieces of candy, I'll wear earrings with minerals in them. I do have one on today. You guys probably can't see that, but there's different. I wear a lot of them that are quartz. This is a purple quartz. It's called amethyst. This is actually called green amethyst. I know it's not purple, but they're related. The minerals that are in there substituting for the silicon are related. This is a green amethyst. This is rose quartz. They just call this diamond quartz or clear quartz. These are citrine. Let me move my mouse. The ones on the bottom are citrine as well. Okay. And citrine has that yellow or orangish color, but quartz is just beautiful. It's not as hard as diamond. It's not as hard as sapphires and rubies, but you can get beautiful gemstone quality quartz crystals out there. So this is really cool. You can kind of see a line going through that there. That means there's just something, some kind of inclusion in that. And we'll talk about that. Now this is a sapphire. I would have showed you my wedding ring. My wedding ring had a big, beautiful sapphire on it with diamonds, but it fell off in class last year. Not in class, but somewhere in this building, my sapphire fell out of my ring because I didn't go and get it cleaned soon enough or often enough. And it's really very upsetting, and I'm still trying to find it. So if you find a sapphire, let me know. I'll give you a reward. But this is a beautiful one, huge. Surrounded with diamonds. They're very popular. This is the Cullinan diamond. This is the largest diamond in the world, 530.4 carats. Diamonds usually, they don't look like this, obviously, when you pull them out of the ground. They are fairly ugly, but they're very, very hard, the hardest mineral in the world. And then some professional cuts them to make them this beautiful. This one, the clearer it is on the inside, the more pure the color, the more expensive it is, the more it's worth. But this is the biggest one ever. This is a diamond. It looks like a sapphire, but it's not. This is called the Hope Diamond. The Hope Diamond has a lot of mystery surrounding it, a lot of legends. And it's people who have owned the Hope Diamond. There's been at least 10 deaths. Maybe not directly related to it, but the people who owned it did experience a tragedy over the past 200, 300 years. Actually, it's been around for longer than that. But there's the secrets of the Hope Diamond. I'll tell you more about that in class. But it's been in a lot of different settings. Like you can see, this is in a necklace. Sometimes it's in a crown. Sometimes it's just a pendant. And so you can do different things. What happened? What in the world is going on? I guess that was it. That might be the last one. So Fig, tell me which ones is your favorite. I guess that was kind of the last. I thought I had more diamonds, more of the Cullinan diamonds. I maybe don't have the most recent, options of my slideshow, but I'll show you guys those in class. So just pick out your favorite one, and you're done with this. And next class we'll probably, after spring break, we'll make some crystals, and we're gonna figure out how to identify minerals. Okay. Thanks, guys. Have a great spring break. I will see you in a week, a little more than a week.